Now that we have our salts, we're ready to construct our molecular orbital diagram. So on the right, here are our salts, A1 prime, E prime, went into this in gnarly detail, right? There's a totally symmetric one and our other E primes. Now we can talk about the atomic orbitals for the central atom. Remember, let's just assume for now this is a second row atom, doesn't really matter, but we're going to have a 2s orbital and a 2p orbital for bonding. The 1s is going to be core, not involved in bonding. S orbitals always have a symmetry of the totally symmetric representation. So for D3H, this is A1 prime. And our p orbitals, we have px, py, pz. What are the symmetries of those? In order to figure that out, we have to go to the character table, right? So here's the character table. You can see x and y vectors transform as the px and py orbitals. So x and y, px and py are going to transform as E prime, and the pz is going to transform as A2 double prime. Let's go back here. That's why we have A2 double prime for the pz and E for the x and the y, px and py. Now, what do? We make bonding and anti-bonding interactions from atomic orbitals that have what? The same symmetry and similar energy. So same symmetry, here we have an A1 prime, here we have an A1 prime. Combine those constructively, everything the same phase. Use a lowercase nomenclature here with the A. It's the first one, so put a 1, 1A1 prime. Check the symmetry of this. If you check the symmetry of this, well, it's just one big sphere, essentially, so that's going to be totally symmetric. Make the anti-bonding interaction. Make one of these, flip the signs of one of them, either the center or the edge, either one's fine. And if you check the symmetry of this, you can do all the symmetry operations, C3, sigma V, perpendicular C2. You're going to get ones across the board. You're going to get back this molecular orbital, so it has a symmetry A1 prime as well. It's anti-bonding, so we put a star, and it's the second A1 prime on the group, on our molecular orbital diagram. That is very nice. From here, what do we have left? All we have left is E, sorry, this should say E prime, by the way. E prime, and there's no E technically in D3H, E prime and E prime. Combine those. So that's the P, X, and Y, and these two salts. So we can combine those. That's going to look like this and this constructively, and like this and this destructively. Okay? Technically, there's a small glitch. You notice these small errors as you go through this. There's a very small error here, and it's almost inconsequential. I hesitate to even bring it up. But this picture here, remember, that's a hydrogen right there where that dot is. That's one of the hydrogens. I'm looking at this picture right here, by the way, okay? That picture is technically just a little off because that p orbital here, that's the px or the py orbital, should be in the center, okay? So it's really going to look like that. And same with this one. This should just be moved up to the center. That p orbital is on the central atom. And while we're here, we'll just mark that as E prime. Okay, it's very small error there. But anyway, so these are constructively. These, I just flipped the order of I just flipped the shading on the P's to make them anti-bonding. And so you're gonna get E prime and you're gonna get E prime star there. What's left is just A2 double prime. That's gonna be non-bonding, so I put an N. So that's a P orbital going in and out of the paper. That's the PZ, it's non-bonding. And that's everything. So, once you get the salts is definitely the hardest part. It's not bad, okay? I think the energies of all these make sense, right? The A1's obviously, A1 prime is lowest in energy here, 1A1 prime, because it came from something that was lowest in energy. Non-bonding is in the center, etc. So let's actually stop there, and what we're going to do next is we're going to use the 3 rules and actually construct the Walsh diagram.